All right, welcome back, everybody. So again, no warm up or homework to go over. So we're going to get right into the notes. I was just talking about ratios and proportions. What comes to mind when I say proportion? Nathan?
Like a ratio, kind of.
Like a ratio. Good. And what is a ratio? We talk about a ratio. Go ahead.
Like how many, like an example would be how many oranges are in a package.
Good. Orange M&M's to total M&M's. Right. It's a comparison of things. Like another ratio would be miles per hour. The amount of miles you travel in 1 hour. Another ratio would be students to teachers. Another ratio would be amount of boys and girls in the class. The amount of people with classes to total amount of students in a class. The amount of, just comparing two quantities. Okay? It could be two completely unrelated quantities or two very closely related quantities. Those are ratios. And then we can say, well, if we know what a ratio is, what we could say is two things are what's called in proportion to one another. When two things are in proportion to one another, that's a really strong statement. We can say that they're equivalent. The ratios are equivalent. Again, we talked about it. A ratio is a comparison of two quantities, where a proportion is showing that two ratios are equivalent to one another. Two ratios are equivalent to one another. Now, I was talking to Mr. Spottelson the other day, and I said, oh yeah, we're going to be talking about ratios. And he goes, oh, they know how to do that. Just tell them to do the butterfly method. Some of you guys know what I'm talking about when I say the butterfly method. Most of you. Basically, what I learned it as is just cross multiply and divide. Cross multiply and divide. So basically, or just cross multiply, really. Basically, all I need to do here is say A times D is equivalent to B times C. See how it looks like a little butterfly? Yeah. That's what they call the butterfly method. A times D is equal to B times C. Cross products are equal. It's called the cross products property, basically. Cross products of a proportion are equivalent to one another. Okay? A times D is equal to B times C. So let's take a look at these first two examples. X over 6 is equal to 10 over 12. X over 6 is equal to 10 over 12. All right, so let's do the butterfly method. Let's cross multiply and divide. Okay? Let's take a look here. First thing I want to do is pair up my diagonals, and then I can say, okay, 12x, x times 12 is 12x, not 12 plus x, 12 times x, is equivalent to 6 times 10. Well, 6 times 10 is 60. See, I can cross multiply, and then I divide. I divide over the 12 over to the other side. So x is 5. You follow me there? Cross multiply and divide. Cross multiply and divide. And this is only when you can set two ratios equivalent to one another. Cross multiply and divide. Okay? Okay? So x is equal to 5. Now, some of you may have said, well, wait a second. What if I get those butterfly wings out of the way, and then I say, look back up here. What's the operation that takes us from 6 to 12? Multiplication by 2. Right? Times by 2. If I do that same operation on the top, because whatever I do to the top, I got to do to the bottom. If I multiply by 2 on the bottom, what multiplies by 2 to get 10? 5. So this here, that's 5. Okay? The cross products are equivalent. Okay, do 2. Do the second one if you haven't already. Some people I see have done it already. That's okay. You did.
Number 21. No. Oh, I meant 27.
Oh,
I
that's
think
you?
yeah.
There you are. Yeah. All right, so let's take a look at this one here. Cross multiply, right? Cross multiply. So we've got p times 5. 5p. 4 times 13. 52. And then we divide that 5 over to the other side. And I believe it's 10.4. Now, in that respect, it would not have been easy to see, we went back on the first one and said, like, oh, can I logically reason that through? Can I do that for number 2? No, that would be a lot harder. I would say, okay, how do I go from 13 to 5? What do I multiply by? Well, that's a lot difficult. It's a lot more difficult than just saying, oh, I multiply by 2. Okay. All right, so that's just generally how to solve a proportion. Remember that in all proportions, cross products are equivalent. So really, the difficult piece to this is just setting up the proportions correctly. Setting up the proportion correctly.
Are you also divide by
The thing with the variable?
Yeah.
Yeah, because you actually end up making your equation where it's just a multiplication, so all I have to do is divide and give it over to the other side. Yeah. So let's take a look here. You take the measurements shown in the diagram. I got a house here. It's 25 feet away from the tree. I got a house that's 25 feet away from the tree. I see here a person standing here with their shadow, 8 feet long, 6 foot tall person. I have a tree, shadow is 30 feet long. Can the tree fall on the house? Is the tree big enough to fall on the house? That's what we're looking for here. So what's my variable? What is x going to represent? The tree. Well, what do you mean, the tree?
Like the tree falling?
No.
Oh.
The height of the tree. The height of the tree. This x is going to represent the height of the tree. Now, can somebody create a proportion? Can somebody create a proportion to solve with x in it? How do we create a proportion with x in it? What do we think?
X over 25?
Nope. Proportion means 2 ratios. 2 ratios equivalent to one another. No?
If you 6, 8, and 5,
Be careful. I want to do 6 over 8. And I do 6 over 8 because this is the height over shadow. But I want to look at the similar triangle here. Do we see the similar triangles there? So now we can see a little bit better. 6 over 8 should be equivalent to what? X over 30. Height over shadow is equal to height over shadow. X over 30. Now, could I set this up differently? Of course. 6 over x is equal to 8 over 30. Guys, am I using 25 in the proportion at all? No, the only thing I care about the 25 is it's showing me it's 25 feet away from the house. That's the only thing I care about there. So let's figure out the height of the tree. So I cross multiply 8 times x is 8x. 6 times 30 is 180. Again, cross multiply. 6 times 30 is 180. 8 times x is 8x. I divide by 8. 180 divided by 8 is, there we go, 22.5 feet. But that's not my answer. That's not my answer to my problem. What is the answer to my problem? Good. The tree will not hit the house if it falls. The tree will not hit the house if it falls. The tree will not hit the house. Okay? Because the space in between is 25 feet and the height of the tree is only 22 and a half. Now, in a couple years, maybe the tree grows another 2.5 feet. We should be a little bit more cautious. But for right now, we can say, no, it's not going to hit. Let's take a look at another one here. Your friend is 5 foot 8 inches tall. And your friend is sitting there casting a shadow that is 12 feet long. So maybe it's later on in the day, long shadows 12 feet long. At the same time, a nearby tree casts a 54-foot shadow. A drone is stuck at the top of that tree. At the very top of the tree, the drone is stuck. Can we use a 21-foot tall ladder? Can we use a ladder that allows you to reach a height of 21 feet? A 21-foot extension ladder to get the drone. Is it possible to reach the drone with that 21-foot ladder? All right. Now, I don't know about you guys.
The interruption. At this time, we need 7th graders, last names beginning with K through M. Please go to the performing arts hall now for your screening. That's 7th graders, last names beginning with K through M. Go to the performing arts hall now and bring your eyeglasses. And that's it. Thanks.
Okay, I don't know about you guys, but I think the last problem was easier to do because it had a diagram with it, right? It had a picture. So let's draw out our picture. Okay, let's become little artists. Your friend is 5 foot 8 inches tall. Okay, so let's draw our friend here. Like I say, if you don't have friends, you can just draw them.
You're talking about yourself, Mr. Maverick.
Our friend is 5 foot 8 inches tall. The shadow is 12 feet long. The tree, which we don't know the height of, has a shadow of 54 feet. And we've got a little drone stuck in the top of that tree. I want to see if my ladder can get to that drone with the very top. And my ladder is a 21-foot extension ladder. So, somebody create the proportion for me. Rose?
5.8 over 12, and then x over 54.
5 foot 8 over 12 is equivalent to x over 54. Good, that's a good ratio. The only thing I would change about what she said is she said 5.8. Is 0.8 equivalent to 8 inches? No. 8/10 of a foot is not 8 inches. Remember, inches are out of 12 inches in a foot. So what I need to do to figure out my decimal point is to take 8 inches out of 12 inches. That's my decimal point. That's my decimal point. Okay? So it's not 5.8, it's actually 5.67. And I'll round to the nearest hundred. So I'm gonna change this now. Instead of 5 foot 8 inches, I'm gonna turn that into 5.67 inches or feet. Excuse me. 5.67 feet. And now we can cross multiply and do it. You got to be careful about that. On Monday, we're going to spend. Excuse me. On Monday, we're going to spend a lot of time going through, kilograms to pounds, fluid ounces to cups, pints to gallons, those types of things, and back again. We're going to be transferring all of that, like kilometers to meters, kilometers to centimeters, and so on. I know you guys did that in science class, but we're going to do that again. Focus on more of the math of it. So it's important to know how to change inches into feet, decimal amounts of feet. So let's cross multiply. We have 12 times x, or just 12x, is equal to 5.67 times 54. So 306.18. 306.18. And now I divide by 12. So x is equivalent to 306.18 divided by 12. And that's going to get me 25.5. I can just round it there. 25.5. So what's my answer? What's my answer, Danielle?
No, the ladder won't reach the grade.
Good. No, the ladder will not reach it. Good. Yes.
You can call me done for this if I'm wrong.
What's that?
But if you had your subscribing friends, if you had your imaginary friend like stand on the top of that ladder, since he's already 5'8", wouldn't that reach?
I can see what you're saying there. But you never really want to be on the very top rung of a ladder. Like you never want to like stand on the top of the ladder. You could like get a broom and bring it up there and like knock it down.
Yeah, but then the drone's gonna break.
Then the drone's gonna break. I know you kind of want to
Then
safely.
you're trying to save your drone. You don't want to destroy it.
Right.
So
Yeah.
it's not gonna break.
The equation says, can you use a ladder that allows you to reach the height?
Well, yeah. Okay. Well, maybe it might be possible, right? I don't know. You don't know. I mean, you could be a 7 foot tall person, right? But if you're 7 feet tall, you maybe a couple rungs down, you can still. I don't know. We'll see.
Just
Right. Or if you're really small, you know.
Thanks for calling me out.
climb the tree.
All right. So let's switch gears. Flip it over onto the back there. Using rates. Now, a rate is just a special relationship between two quantities. It's a ratio of two quantities using different units. For example, and the rates that I love to give examples on are always speed, like meters per second, like feet per second, miles per hour, kilometers per hour. Okay. But you can also have different varying rates, but usually it's over time. So 10 meters per 1 second could be, now these are all the different ways that we could write it. 10 meters per second, 10 meters per second, or we could write it like this as well. Now, what we're going to be doing here is using rates and using ratios to kind of back up an argument or back up a statement. Like for example here, this diagram shows statistics for a baseball pitcher. Use rates to compare the pitcher's performance in 2019 to his performance in 2020. So maybe I'm the pitcher and I'm like, I want a new contract, I want a better contract. I want to show that I have been improving from 2019 to 2020. Well, how do I show improvement? What statistic is going to make me look good here? So that's what we have to see. Now, the book does not direct you on what ratios to find. So what we're doing here is we're directing you a little bit. We're saying, okay, compare strikeouts per walk. And as you'll notice here, on the homework tonight, everybody look up on the homework board, and this is on Canvas as well. On numbers 7 and 8, which are these types of ratio problems, I'm telling you how to compare the two things. Like number 7 is a comparison of two schools, and we're asking you to compare the schools using a student-to-teacher ratio. And number 8 is a table of sales, and we're saying, okay, compare the sales made based on sales attempted. Okay, use that ratio to compare the two things. So what we're going to do here is say, okay, let's find the statistic of strikeouts per walk. Strikeouts per walk. Let's look at what happened in 2019. How many strikeouts in 2019? 100. 100. How many walks in 2019? 29 walks. Okay, the strikeout to walk ratio is 100 divided by 29, which is just 3.45. 3.45. And that is, and I'll abbreviate, strikeout per walk. So for every one walk that this guy pitches, he's got 3.45 strikeouts, which I think is pretty good. 3.45 strikeouts per walk. He's ending an inning with 3 strikeouts for every walk he produces. Okay, let's see what happened in 2020 though. Let's see if he shows improvement. Well, in 2020, maybe the baseball team's like, wait, you're not going to improve. You only did 73 strikeouts in 2020. You had less amount of strikeouts. But then you can come back to them and say, okay, well, but if you compare it to my walks, and I take 73 out of 20, the number of walks that I had, that's a better ratio. You can say, well, wait a sec. I had a better strikeout per walk ratio. I struck out more batters than I walked in 2020 than I did in 21. Okay, it's all about spinning your argument in the right direction and saying, okay, well, wait a sec. No. It's not all about the quantity. It's about the ratio. Okay, I went down in total amount of strikeouts, but my ratio was better. Look, and you can really see that by the innings. Like maybe this guy got hurt in 2020 and he pitched 20 less innings. So obviously he's going to have less strikeouts. And then let's take this statistic. The amount of earned runs per inning. This is not truly ERA because ERA calculates in a total of 9 innings. But this is just earned runs per inning. Earned runs per inning. Let's compare 2019 to 2020. So, and this is, for those of you guys who don't know, earned runs is basically like the amount of runs that the other team is scoring on that pitcher that the pitcher's at fault for. Right? So it doesn't count any errors made or any weird things happening in the outfield. All right, so 2019. Earned runs is 19. Innings is 70. Okay. 19 out of 70 is 0.27. 0.27. And that's earned runs per inning. And again, this is not ERA. ERA, I would have to multiply that by 9, which is actually so good. Okay, now in 2020, earned runs, 15. Innings, 50. Because less innings to pull from. 15 out of 50, okay, 0.3. Earned runs per inning. Now, so maybe the baseball team is going to come back and say, no, we're not going to pay you. We're not going to give you a raise. You're allowing more earned runs per inning in 2020. Okay? It's all about how you spin it. You could show statistics to prove any kind of point. Okay? It's all about how you dig it up, and it's all about how you compare it to one another. Okay? So, go ahead and take a look at the next problem. Compare the statistics of shots attempted, points per shot attempted. Compare points per shot attempted and make a decision about game 1 and game 2. Go ahead and do this one. Compare points per shot attempted. Compare points per shot attempted. And compare game 1 and game 2. You put back my calculator yesterday, right?
And the one with the paper.
Yeah. That's right. I blame my later periods. I think they're stealing my calculators.
Should we round to 10?
Oh,
I would go to hundreds. So in game 1, I had 37 points and attempted 47 shots. So 37 out of 47, 0.79, 0.79. 37 points out of 47 shot attempts. Yes?
Since each basket counts as 2 or 3 points, would you divide that?
Nope, because this is strictly points per shot.
Oh.
Points for one shot. Okay. Now, in game 2, let's see what his ratio was. Okay, 26 points. Okay, for 26 shots. That's a 1 point per shot attempt. So what can we say about game 1 and game 2?
He was more efficient in game 2.
More efficient in game 2, right? Yeah. In game 2, he had a higher point per shot attempt ratio than in game 1. All right, that's it for today. Let me turn off the video. So long, everybody watching along at home.